Okay, let's move on to the next question, which is number 2 over here. I've already copy pasted it to this page, along with the instructions. So, the question asks us to prove whether or not the language is regular. If it is regular, make a DFA for it. If it's not regular, use the pumping lemma to prove that. So, this language, let's just first go over what the language is. So it's all languages over alphabet alphabet 1, where the strings are in this form. So 1 to the power of 2n. So 1 to the power of an even number. So what that means is that it's all strings with even length. So all strings containing an even number of ones. That's what this language is. Now the first thing to think to yourself is, can I make a DFA for this? In other words, is this regular? Well, the answer is yes, because there would only be two states that you need to keep track of. The state where the number of ones you've seen is even, and the state where the number of ones you've seen is odd. So you can make a DFA for this. And if you were to try and prove it's not regular, you would not be able to reach a contradiction no matter what string you pick, and so you'd just be wasting all your time. So let's try and make a DFA for this. First, we have a state to represent an even number of ones seen so far. So, okay, that looks a bit weird. Let me just redraw that. Q even. Okay, there we go. So this state will represent an even number of ones. So it will be our start state because 0 is an even number. Then we have a state, sorry, then we have a state for an odd number of ones. So if we have an even number of ones, so we see a 1, we've now seen one more 1. And that means we've seen an odd number of ones. If we add an odd number of ones, and we see another 1, then now we've seen an even number of ones, because an odd number plus 1 is an even number. So that's it, this is the DFA for the language. We have two states, even, odd, and we alternate between these two whenever we see a 1. So this is the DFA for this language, and it works. Let's go over some example strings just to convince ourselves. So this has 3 ones, therefore it's an odd number. This has 2 ones, therefore it's an even number of ones. This has 4 ones. So this should be a reject, this should be an accept, and this should be an accept. Let's see if that's true. So for this string over here, we start off in Q even, we read a 1, we go to Q odd, read another one, go to Q even, read the last one, go to Q odd. And so the string is rejected because we're not in an accept state. So this works as expected for this string. Let's try it for this one. Start in Q even, read the string, read the letter, go to Q odd. Read another one, go to Q even. It accepts that string, which is what we expected, so it works for that. Let's now try this one. Start in Q even, read a 1, go to Q odd. Then read another one, go to Q even. Read another one, go to Q odd. And then back to Q even on the last one, which is accepted, so it works as expected. So this is the answer to the question. We've constructed a DFA for the thing because we thought it's regular. Now, let's go over what would happen if you try to prove it's not regular. So let's pretend like it wasn't regular and we're trying to prove that case. So we assume it's not regular. Then we do all this boilerplate. So our goal here would be to find a string in the language with this length and try to find a case where the string has no possible breakdown where all three of these properties hold. So every breakdown leads to an issue. So let's take a string. Because this language is so simple, there's only really a few like strings you could take. they're all basically going to be the same. We could take 1 to the 2n, we could take 1 to the 4n, just any even number. So no matter what string you pick, xy will only contain 1, right? Because that's the only character in the alphabet. So this string is in the language because it's even length. So let's write that. And its length is what we needed because it's 2n, which is greater than or equal to n. So now let's think about the different ways we can break down the string that could lead to different behaviors when pumping. So one way of breaking down the string is where y contains an odd number of ones. So I'll just write hashtag to represent number. Okay, if y contains an odd number of ones, and then we pump either down or up, we're removing or adding odd numbers of ones to this string over here. And if you know from maths, an even number plus or minus an odd number is an odd number. And so by pumping this string with a breakdown where y has an odd number of ones, we will reach a contradiction because the string will no longer have an even number of ones, and so the third property will be broken. So this breakdown would lead to contradiction. But that does not disprove the regularity of the language. This doesn't show that it's not regular, because the pumping lemma says that there exists a breakdown. So there has to be just one breakdown where it works. If you show a breakdown doesn't work, then it might not cover all the cases, right? Because the other case is that y contains an even number of ones. We still haven't considered this case. So just showing this one leads to a contradiction doesn't cover all the possible cases. So let's think about the case where y contains an even number of ones, right? If we pump the string up or down, we will be adding an even number of ones or removing an even number of ones to the string. And an even number plus or minus an even number is another even number. And so with this string, with this breakdown, where y contains an even number of ones, pumping it satisfies this property. And so we don't have a contradiction. So we've found a breakdown for this string where the pumping lemma is satisfied. And so we haven't reached a contradiction. So we can't use the string. And this exact situation is going to happen no matter what string you chose. If you chose 4n, you'd reach a similar issue where one breakdown still works. If you chose 6n or any positive n, you'd reach the same issue. And so trying to use the pumping lemma for disproving the regularity of this question is just going to lead you in circles forever. So please make sure that when you read the question in the exam, you first think about whether or not it is regular, if the question is open-ended. If the question straight up asks you to prove a language is not regular, then you can already assume that it's not regular and just use the pumping lemma. But if it's more open-ended like this, then you need to think about the fact that it may still be regular. Okay, so that's it for this question.